We will start the session. Okay, so I think last week we discussed up to the transformers theory parts as well. So here today we'll discuss about the last part, which is about the national grid or the national grid supply, and then we'll move on to the past paper discussion section. Okay, so just give me a minute to share my screen. Right. Right. So, and also I have already uploaded this PDF in the WhatsApp group, so you can leisurely refer them. And remember, this can be used as a short note, and no need of printing. But if you need, just imagine it's like if you think this is a good short note and it's better to refer a hard copy of this thing. So then you can print it and refer it, right? Okay, so so far in this unit, we discussed about these sections. What are the magnetic materials, non-magnetic materials, and what is meant by magnetically hard, magnetically soft, like those stuff, right? We discussed about those stuff. And yeah, and we discussed how to draw the magnetic field lines and what are the what type of what do you call that? What type of experiments can be conducted to identify the magnetic fields when it comes to like their direction, and also uh, just to identify the magnetic field lines, then we can use the iron fillings. But if you need to identify the magnetic field direction, then you need to use the plotting compasses. So here, those things are not mentioned here, but there are some important facts mentioned when it comes to a magnetic field, the magnitude or the strength of a magnetic field. So it will be depending on the number of lines or the magnetic field lines going through a certain surface area. And here it is mentioned about an uniform magnetic field. So when it comes to a uniform magnetic field, the magnetic field lines will be they will be parallel to each other. So parallel means those two lines, right? Between those lines, you will be having equally spaced section. Then we discussed about how the electricity will be generated when there's a magnetic field. So we use the right hand swirl rule here, right? Right hand swirl rule. So here the only changing factors are the current, the direction of the current, and the magnetic field. So here we are using capital B to get the magnetic field. Okay. So you can go through these notes, and we discussed about solenoids as well. And then we discussed about the Fleming's left-hand rule, so how to use it, and few applications were discussed. And so in here you can see instead of force, it is mentioned as U, but you can use F here, right? So it will be giving us the force, magnetic field, and the current direction. So you can easily remember it by FBI, right? So these are some sections that we discussed, and here a comprehensive note is given, a short note type of a thing. So by increasing the force, we can increase the magnitude of the current which is generated, or increasing the force. To increase the force, we can use a stronger magnetic field. And if we need to reverse the force, then we need to reverse the current direction, or we need to reverse the direction of the magnetic field, right? So we discussed about those things, and the motor effect as well, how the motor is being working, and to in order to increase the turning effect, what are the factors that can be changed. So we discussed about those stuff. And about these sections as well, the electromagnetic induction part. So when it comes to induction means generating, or formulating something under an external influence, right? Under an external influence. So then maximizing the induced voltage, so we can move the wire more quickly, and we can use a stronger magnetic field, and we can increase the the length of the wire by having a coil or something like that. Then we can generate more induced voltage. So we discussed about these things in the last sections. And here, applying the induction or the power generation when it comes to the, like power or voltage generation. So here we can use two different methods. So the first one will be rotating a permanent magnet. So in this case, the magnet is permanent with a stationary coil, right? The thing that I want to emphasize is that we are rotating a magnet, right? We are rotating the magnet, but the coil is stationary, right? So as you can see in this diagram, the coil is stationary attached, and here in this case, the magnet will be rotated. Okay, magnet will be rotated. So because of that, what will happen? These magnetic field lines will be cut by these wires. And the second option is that you can rotate the coil, right? Rotate the coil while the magnet is being a stationary object, right? So first one, magnet is being rotated and the coil is stationary, coil is fixed. But the second one, the coil is stationary while the magnet is, sorry, the coil is rotating. So as you can see here, the coil is the one which is going to be rotated while the magnet is placed as a stationary object, right? So you can approach with these two methods. It doesn't matter. So actually the method depends on the equipment that we are going to make, right? So whether we can rotate it is whether it is easy to rotate the magnet or it is going to be easy to rotate the coil or something like that. Okay. So here main thing the same theory part that follows here is that where there's going to be a rotation process. So therefore, the magnetic field will be cut, right? So magnetic fields are being cut. So therefore, there will be an alternating voltage generated. There will be an alternate voltage generated. Then you can just go through these nodes, right? And finally, we discussed about the transformers, right? Just forget about these topics, right? These headings. So when it comes to transformers, so last week we discussed how to prepare a transformer and like step up transformers and step down transformers likewise. And also, so if I label these diagrams of the primary coil, the voltage which is having in the primary coil, so it will be known as VP, right? We'll label it as VP. And the current in the primary coil, it will be IP. And when it comes to secondary coil, the voltage output that we can take, I label it as Vs, and the current is going to be Is. Current is going to be Is, right? And so the primary coil, alternating voltage produces an alternating current in the primary coil, right? So that is what is being produced. And then the soft iron core, right? This creates a constantly charging alternating magnetic field trapped within the soft iron core. So that is the main reason that we are using this type of a material there. Then the third one, the change in magnetic field links with the secondary coil, inducing a new alternative voltage. So that is known as generator effect. So that new voltage will be the Vs value, right? It will be the Vs value. So the main purpose of using a transformer is that explosively change to the size of an alternative voltage, or we can say in order to change the value of the voltage. So whether we can we can increase the voltage output or we can decrease the voltage output, right? So when it comes to these transformers, right? When it comes to these transformers, so I might have mentioned that the voltage, right? Voltage in a coil, whether it is going to be the primary coil or the secondary coil, so that will be directly proportional to the number of turns in the coil, right? Number of turns in the coil. So the voltage is directly proportional to the number of turns in the coil. So by using it, right, we can get an idea. We'll say we can get an equation. So I'll add up page and yeah. So something like this. So as I mentioned, the voltage is directly proportional to the number of turns in a coil. So therefore, we can say the V primary is directly proportional to N primary, which is the number of turns in the primary coil. So this is the first equation, and the secondary voltage is directly proportional to the number of turns in the secondary coil. So this is the second equation. So if we need to link, or if we need to have an expression which we can use for the calculations, then we need to link these two, right? So therefore, finally, I can say Vp over Vs, which means the primary voltage over the secondary voltage, right? Primary voltage over the secondary voltage, the ratio is going to be equal to the number of turns ratio, right? So this is your last equation. So this is the thing that you need to remember. This thing will be asked in the exam as well, right? They might ask you to write the relationship. So in that relationship, you can use the word equation, or you can use this equation as well. But remember, you need to use the correct symbols here, right? You need to use the correct symbols with the N and P, those values, okay? So remember that point. Otherwise, you will be getting different answers, different values or something like that, right? So in that case, my advice is that, like, it's better to use the word equations, right? Word equations. And so this is the first relationship that you need to remember when it comes to transformers. And the second one is that, so we have an equation for power, right? Power equals voltage into current. Voltage into current. Voltage into current. So therefore, P equals VI, right? And so there's an assumption in this thing, right? So we are going to assume that this transform is 100% efficient, right? 100% it is going to be efficient. So efficient means there's no wastage of, or no wastages of power. It is not going to be wasting into, like, different sort of waste materials, like waste energies, like. So we are assuming that it is 100% efficient. So if it is 100% efficient, then we can say the input power, right? The input power is going to be equal to the output power, right? Input power will be equal to the output power. So which means, so therefore we can say Vp into Ip, which is primary voltage into primary current, will be equal to secondary voltage into secondary current. So this is your second equation that you need to remember when it comes to transformer related calculations, right? When it comes to transformer related calculations. So remember these two equations. Most of the time they will ask you the relationship, and there will be some situations where we need to calculate these values. Okay. So today we'll focus on the calculation part as well, right? So these are the connections, right? No need of knowing how to get these values or how to get the answers, but remember the assumptions that we are using, right? There are some situations where they consider about the assumptions as well, right? Okay, then yeah, then the transformer diagnostics. So as I mentioned, there are two types of transformers. So step-up transformer mean, just imagine something like this. Vp value, the primary voltage is a low value. And so you need to increase the voltage in the secondary one. So in order to increase that, you are using step-up transformers, which means you are providing a small voltage, but you are getting a higher voltage value from the output. And as in the other one, that is step down. So VP is at a higher value, then Vs a low value. So you are decreasing the voltage value, right? So here it is being increased and here it is being decreased. It is being decreased. So the construction type. So number of turns on the secondary, more number of turns. So as I mentioned, right, the voltage is directly proportional in the voltage is directly proportional to the number of turns in a coil, right? The voltage is directly proportional to the number of turns in a coil. So therefore, if you need to have a higher voltage, that means you need to have a higher number of turns as well, right? So therefore, more turns on the secondary. So which means if we draw the diagram, right? If we draw a simple diagram, so what will happen? VP will have low turns, but VS will be having more turns like this, right? And for step down, what will happen? VP will be having more turns and VS will be having few turns like this, right? So remember that. And the voltage output is given. So voltage increases and the voltage decreases. And there are some applications given. So if you need to transmit power through cables to reduce the power loss, right? So this is actually, so remember this point, I will explain it in the national grid section, right? So if you need to transfer power, right, to a different place, then there will be a power loss, right? Because of the resistance of these wires and cables and all the stuff. So therefore, you need to give a higher voltage value into the system. Otherwise, the other end will receive a low power, right? So therefore, we need to increase the voltage and supply it to the transfer mechanism, right? And here, safe use in homes. So we all know that in Sri Lanka, the national grid, right? So those bigger lines, they will be having like something around 33,000 voltage values. But when it comes to our household home appliances, right? So most of the electrical equipments, they will be using just 230 voltages, right? So which means like that 33,000 voltage must be decreased to 230 voltage, right? So these are the practical situations where we use these type of transformers, right? And here we can see the equations are given there, right? And so this is the power grid, right? So when it comes to the power grid, mainly there are 5 sections that you need to pay attention, right? So the first one is where you are going to generate the power. So this generation of power, so it can be either rotating a turbine, right? Most of the time it will be rotating a turbine. So in this turbine, what you will have is that there will be a magnet and it will be rotated. So because of the magnet rotation, the magnetic field lines will be cut and therefore there will be an induced power, right? Induced voltage. So that voltage, right? That voltage will be directed towards the first transformer. So this first transformer, still this section, right? This section 1 and 2 still at the power station, right? So these are still at the power station, right? So just imagine you generated only 100 volts. So now what will happen? You are increasing that power. So here we are using step up transformer, right? We are using a step up transformer, which means this 100 voltage will be increased to, let's say, 33,000 voltage, right? 33,000 volts will be increased. Then it will be supplied to the wire or the cable system. So here in this cable system, you will be having 33,000 voltage value, right? So it will be transmitted through the island or uh, up to the place that you need, right? Then what will happen? Then the fourth step, so here you will be receiving 33,000. So you need to downgrade it because here in the household systems, we are using normally 230, 240 voltage. So this 33,000 must be downgraded or must be decreased to 230. So therefore, the fourth step will be the step down transformer, right? So in the step down transformer, what will happen? This 33,000 will be decreased to 230, and we can use that 230, right? So these are the main five components of the national grid. Okay, these are the main five components of the national grid. So when there's a question related to national grid, then you need to mention about all the five steps, right? All the five components. And as I mentioned here, the transmission part. So this is the most important one. So when transmission occurs, right? So there will be like these wires will be having some sort of a resistance, right? Some sort of a resistance. So when you are experiencing a resistance, there will be a wastage of power, right? So these cables can be heated. So we don't need the heat energy. So therefore, there's a little bit of a resistance. So in order to minimize that wastage, right? So just imagine something like this. You need 100 volts, right? But the wastage is 50 volts in the path. So then at the initial point, if we supply 100 volts, then what will happen? So 50 volts will be wasted. So therefore, the consumer will receive 50 volts, right? The remaining 50. But he needs 100. So therefore, what will happen? We need to provide that wasted value as well. So which means here we need to supply 150 in the initial supply chain. Okay. So remember that point. Okay. So this is the power grid uh, theory here, right? So remember the important stuff. So as I mentioned in the power grid, there are five components, and you need to remember those components where we have the step down transformer and the step up transformer as well, right? Okay, so yeah, tell me whether you got it or not. Just use a thumbs up reaction, then I can move on to discussion of the papers, the questions actually. Yeah. Is there any section that I need to discuss once again? Right. Okay, so we'll start discussing of the electromagnetism past paper questions. So as I mentioned, so I'm not going to focus more on the smaller stuff, but yeah, I'm going to discuss about the most important questions here. Mm, right. So just give me a minute. I need to figure out the question. Right. If you have the tutorial with you, you can start question number 10. Question number 10. Tell me whether you have completed the tutorial or not. Like, so for each and every question, if you did not complete it, then I will give you like few more minutes to complete it, to go through the question. Otherwise, there's no point of me discussing the question tutorial, right? So, you guys need to have an idea about the questions that we have, right? So tell me whether you have completed the tutorial, or uh, do I need to give you like a small time to go through the question and to try. Okay, so the first page. The first page, you are having this sort of a diagram, a motor. I uploaded that question tutorial last week, okay? Right. So in the tutorial, we'll start with, wait, Okay, so we'll start from question two then, right? Question two. So here we have a power supply and all the stuff given. Describe how to find the shape of the magnetic field produced by the loop. So when you're going through these sort of questions, you can underline the most important parts, right? So here they are focusing on the shape, right? They're asking the shape, not any directions or anything like that. So therefore, what will happen? We just need to focus on how to get the shape of the uh, magnetic fields. Okay, right. So in order to get the shape, uh, we can just use the iron fillings. Uh, yeah, just give me a moment, then I'll share the tutorial. Okay, just give me. I have shared the tutorial in the group once again, right? Now see whether you can download it. Now it's okay, right? I think you can open the file. Okay. Right. So give it a try for question two. I'll give you a few more minutes. Describe how to find the shape of the magnetic field produced by the loop. So we are dealing with the shape. Then you can use that iron using iron fillings, right? Iron fillings experiment, right? So you need to describe it. They are offering 3 marks there, right? Then diagram two. Sorry, the part B question. Question part B. Question part B. So the diagram two shows the view from above the card with two cross sections of the loop of the wire. So this dot, it represents the current is going out of the page, which means like it is coming towards you. And the cross, it refers to current is going into the page. On diagram 2, draw the magnetic field produced by the two cross sections of the loop of the wire. Right. 4 marks are allocated there. Right. So now what they are focusing is they have given the current direction, right? I is given, current direction is given. And they are asking magnetic field direction, right? So if it is just I and B, current and the magnetic field direction, then we are using right hand swirl rule, right? Right hand swirl rule. And if it is, remember, if it is current, if it is the magnetic field direction, and any sort of a movement pattern or a direction, we'll go through those questions as well. So if they are dealing with three factors, then we are using the Fleming's left hand rule. Okay, so remember that point. So in this case, we are only dealing with the current and magnetic field direction. So therefore, we are using the right hand swirl rule. So what is the swirl rule? So if this is the current direction, so the other fingers will be giving you the direction of the magnetic field. So something like this. Okay. Right. So now if I label this one to be A, this is to be B for my explanation, right? So from the position A, the current is coming towards you, which means you need to place the thumb pointing towards you, right? You need to place the thumb pointing towards you, which means then you will be getting the other fingers, right? Will be having a direction like this. Okay. So therefore, around A, this is wrong here, right? I'm going to erase it. So here you will be getting a magnetic field like this. And if it is B, so at B, what will happen? The thumb is pointing away from you towards the paper, right? It is pointing towards you, pointing away from you towards the paper. So now you can see all the other four fingers are rotated in the other way around. So in the clockwise direction. So here you will be getting the magnetic field in this direction. Okay. So at least you need to draw 4 lines, then you can get the maximum of 4 marks. Okay. Now tell me whether you got any sort of a question related, like any trouble related to detecting these, determining these directions? No, right? If it is okay with you guys, then we'll move on to the next question. If I need to explain it once again, just tell me, okay? Right. Then the third part, these diagrams show the magnetic field acting on a cross-section of wire when the current is in the wire is out of the page, right? The current is in the wire is out of the page. So here, these are the wires, okay? These are the circular diagrams are the wires. So in those 4 situations, you can see that the current is coming towards you, right? The current is coming towards you. So in this setup, you can see that force, magnetic field, and current. So current is pointing towards you. So which means 3 factors are being considered. So if it is 3 factors are being considered, then we are going for the Fleming's left-hand rule, right? We are going for the Fleming's left-hand rule. So in the question, which diagram shows the correct direction of the force acting on the section of wire due to the magnetic field? Okay, so in here, you need to use, right? You need to use the Fleming's left-hand rule, right? Fleming's left-hand rule. Then you need to judge the force direction. So you can use it for, if we are using for A, so the thumb will be giving you the force, right? Current will be the middle finger, and the magnetic field will be the index finger. So if I get this one, so this is going to be our correct answer, right? There's no need of uh, checking the other ones. Yeah. So the answer will be A, right? Do I need to explain it once again? Yes.
No, sir.
Right. Good. Okay. Then the magnetic field acting on the cross section of the wire is produced by the current in the other side of the loop of wire. Explain why there is no effect on the direction of the force on the cross section of the wire when the direction of the current in the loop is reversed. Why there's no effect on the direction of the force when the wire direction of the current is in the loop is reversed. So what will happen? So if you reverse the direction of the current, so now current direction will be going towards the page, right? And the magnetic field direction will be like this. So if you once again use the Fleming's left-hand rule, right? Now the middle finger will be pointing towards the page, and the index finger will be pointing downwards. So now you can judge and see that the force direction is in this way, right? So if you reverse the current direction, the force will be reversed as well. So what will happen? The previously generated force and this force will be cancelled out because they are having two different directions. They are having two different directions. They are having two different directions. Okay. The resultant value will be 0. So you need to mention about that thing, right? So actually an easy question. Okay. Then we'll go for another section here. Yeah. Question number 8. Small theory discussion question, right? Question number 8. So this question is about bar magnets. Describe an investigation to show the shape and the direction, right? Show the shape and the direction of the magnetic field for a bar magnet. Show the shape and the direction. So if it is just shape, then you can use the iron fillings. But now we are dealing with the direction as it. So which means you need to use the plotting compasses, right? Plotting compasses. So you can just explain about the plotting compass experiment, right? So I'm not going to waste time on that. Okay. Then part B, a bar magnet is used in a bicycle dynamo. The diagram shows a cross section of the bicycle dynamo. So you can see there's a rotating wheel and spindle that is connected to the bar magnet, and the rest you have the iron core, and then that wire, the coil of wire will be uh, connected to the lights. Okay. The dynamo has a rotating wheel that presses against the tire of the bicycle. Okay. The rotating wheel is connected to a bar magnet by a spindle. When the rotating wheel spins, the bar magnet also spins. Yeah, we know about that thing, right? So when the bicycle tire goes in this direction, what will happen? So this will be rotating like this, right? It will be rotating like this. So which means the cap will be rotating like this. So once the cap is rotating, the spindle will also rotate. So the bar magnet is connected to the spindle. So therefore bar magnet will be also rotated like this, which means the magnetic field lines will be eventually cut by the iron core, right? It will be cut by the iron core. So therefore there will be a power generated. So the dynamo is connected to the lights on the bicycle. Explain how the dynamo causes the lights to turn on when the bicycle is moving, right? So the bicycle is moving. So same thing I explained it, right? So when the bicycle is moving, what will happen? The tire will be moving forward like this. The tire will be rotating, and therefore the head of the dynamo will be also rotated. So once the head is moving, what will happen? The spindle will also move, right? It will be also rotating. So since the bar magnet is connected to the spindle, the bar magnet will also rotate, right? So that is the fourth point. So once it is rotating, the magnetic field lines will be cut by the iron core. So therefore, there will be a power generated in the coil and will be directed towards the lights. So therefore, when the bicycle is moving, what will happen? There will be a power generated, and it will be giving the power to the bicycle light, and it will be it. Okay? So these are the points. Right. Then suggest a disadvantage of using the dynamo to power the bicycle lights. So what is the disadvantage? Now think and tell me. So this is just one answer, one score question. So the answer is given in the previous question actually. See, dynamo causes the lights to turn on when bicycle is moving. So if it is not moving, what will happen? If it is not moving, the tire won't be rotating like this, right? So here you have the cap here. So if it is not moving, then the tire won't be rotating. So if the tire is not moving, then the cap of the dynamo, the touching part will be also won't be rotating. So which means eventually the bar magnet will be at a stationary position. So there's no point of having the bar magnet at a stationary position, right? Though there are magnetic fields. So remember, if you need a voltage or a power to be generated, then definitely the magnetic field lines, right? Magnetic field lines must be cut, right? They must be cut by the iron core. So this is the basic rule. This is the basic foundation, right? Still, you're just imagine, still you are having the bar magnet having magnetic field lines, but it is not being rotated, right? So which means the magnetic field lines are like stationed at a specific phase, though there's no cutting of magnetic field lines, so therefore there won't be any power generated. There won't be any induced voltage or anything like that. Okay, so that is the answer for this question, which means if the bicycle is not moving, so the lamp won't be working, right? The lamp is working, but there won't be any power supplied to the lamp. That is the answer, right? Got it? Easy questions. You need to think a little bit, okay? Right. So here, these are PR paper questions. So which means they will be focusing more on the theory related stuff, right? So they are not focusing on the calculation stuff most of the time, which means like any of the student can just apply the numbers and get an answer. But in most of the PR papers, they will be testing the theory knowledge, whether the student uh, knows or whether the student is having the theory knowledge or not. Okay. Right. Then, yeah, uniform magnetic field lines. Question 9, no need of discussing it. Again, a theory question, but a recent question paper, right, from 2023 January. Mm, right. Then, okay, so we'll discuss this question, question number 10. So I will give you a few minutes, right? Question number 10. I will give you a few minutes. You can try it. And once after you have finished, a few minutes means like I will give you 2, 3 minutes. You can try it, right? Once after that, I will discuss it. Otherwise, no point of like, I am just discussing the questions. You haven't even tried that, right? So just use 2 or 3 minutes, then I will discuss the question. Okay, so a battery supplies a voltage of 12 volts at a current of 0.25 amperes to the fan. So which means you have the voltage and current. You can calculate the power value. Uh, the fan is switched on for 12 seconds and the fan gains 25 joules in kinetic torque. Calculate the efficiency of this energy transfer. Calculate the efficiency of this energy transfer. Right. So when it comes to efficiency, right, efficiency percentage value. So it will be the output power over the input, the total input power multiplied by 100. So in like instead of power, you can use the energy value as well, right? So if it is power, then it will be P equals VI. And just imagine we are multi. So power means energy over time, right? So if we multiply time over here, then we will be getting the energy value. So you can get energy by multiplying P into T. So which means it will be VIT. So here you can see the time is also given, right? So the fan gains 25 joules in this kinetic energy store. So the uh, efficiency value will be equal to 25 joules over 12 into 0.25 into 12 seconds and multiplied by 100%, right? Then you will be getting an answer. So it will be, here you can get, this is going to be 1 over 4. Here it is going to be 3, which means 25 over 36 multiplied by 100. 25 over 36 multiplied by 100. So the value is going to be something like 69.44%, right? 69% 44. Right. Then the diagram shows a part of the electric motor inside the fan. Okay, so now when you are having a question like this, so first of all, you need to like make some sketches in this diagram, right? So you need to scribble this actually, right? So first of all, identify the direction of the magnetic field. So here you can see North Pole and South Pole is there, which means the magnetic field will be from north to south like this, right? And the current direction. So here positive to negative. So which means the current will be moving like this. So here in the XW axis, you can see current moving in this direction. And here it will be like this. And from Y to Z in the other way around and returning to the minus axis like that. Okay, so these are the things that you need to figure out. So explain why the coil starts to rotate when there's a current in the coil. Explain why the coil starts to rotate when there's a current in the coil, right? So here we have current, we have current, we have the magnetic field direction as well. So they are asking why the coil is rotating. So in order to rotate, then there must be a force as well. So here we are dealing with three factors, so which means we are using the Fleming's left hand rule, right? We are using Fleming's left hand rule. Okay, so in order to use the left hand rule, so all the components IBF or FBI components must be perpendicular to each other, right? So if we consider about, I use another color. So if we consider about this X and W line, right? So the current direction is in this way, right? And it is on the magnetic field. So the current, so I'm focusing on X, W line, right? So the current direction like this, and the magnetic field direction is like this. Now we need to judge what is the direction of the force. So FBI, index finger is the B value, middle finger is the current direction. So the generated force will be downwards like this. And if we consider the next line, so for X and Y, can we use the Fleming's left hand rule? For X and Y, we cannot use the, uh, we cannot use I'll write it compactly. So we cannot use Fleming's left-hand rule. What is the reason? So here you can see the current direction, right? The current direction and also the magnetic field direction both are falling under the same direction. So in that situation, we can't use it, right? So then we can follow y to z axis, y z axis. So the current direction in this way, the magnetic field direction in this way. Now we need to guess the direction of the force. So FBI, yeah, you can see the force is upwards. So which means finally we can get the direction of the force. So here for for XW, the force is downwards, right? So the force is downwards. And for XY axis, there's a force being applied upwards like this. So eventually what will happen? This way, this will rotate in this direction, right? It will rotate in this direction. Okay, right. So you need to explain those points, right? Do I need to explain it once again? Yes.
Sir, can you explain how that coil turns that side?
Yeah. So here we can see the coil is something like this, right? So there's a force being applied in this direction and there's another force being applied in this direction. But here, this is the rotating axis. So which means this will be rotating in a direction like this, right? Along this axis. Something like, so we discussed about the turning effect of these, rods and all the stuff in the first unit. So that is the same theory applied here. So the direction of the force is something like this, right? Eventually, there's a force applied like this on the wires, right? If it is in two different directions, then there won't be any rotation. But in this case, you can see the direction of the current. That is the main thing that is determining the rotation, right? So here you can see the current direction is being changed, right? Or in opposite direction. So which means eventually the force direction will also be opposite in each and every cases, right? So just think what will be happening when you change the direction of the current. Okay, so that is to be explained here. And remember this point, right? So for X and Y, you can see the current and the magnetic field direction both are falling on the same direction. So therefore, they are not perpendicular to each other. So therefore, there won't be any current generated on the X and Y line. Okay. Then which side of the coil moves vertically upward? Vertically upwards. So it will be Y and Z, right? It will be Y and Z, right? Then,
Sir, then can you tell what's the answer we should write for that one?
yeah, so you need to explain these things, like explain why the coil starts to rotate when there's a current. So first you need to explain the force, the direction of the force generated on XY section. You need to, like, you need to use the Fleming's left-hand rule. So just tell something like this, by using the Fleming's left-hand rule, the force generated, the direction will be downwards. And if we consider about XY, we cannot use Fleming's left-hand rule. So therefore, on that section, there won't be any force generated. And the final part is going to be from Y to C section. So if we use the Fleming's left-hand rule, then the generated force direction will be upwards. So which means eventually this will be having a downward force. This section will be having an upward force. So what will happen is that it will be rotating in the anti-clockwise direction like this. It will be rotating in the anti-clockwise direction like this. So that is the thing actually that you need to discuss, right? That you need to explain. Okay,
Okay, sir.
right. Then right. This question, no need of going through all of it. Question number 11 and question number 11. mm, Question number 11, part B. Question number 11, part B. So here, this question, right? So the current in the wire is turned off. Diagram 3 shows the wire placed in a uniform magnetic field. The current is now switched on. Draw an arrow to show the direction of the force on the wire. Only the previous cases, no need of the previous cases. Just go through this one. The current is now switched on, so there's a power supply, and here you can see there's a small arrowhead. So which means this section will be this part will be positive end, this will be the negative end. So which means the current will be going in this direction. Okay, right. So draw an arrow to show the direction of the force on the wire. Right. So first of all, identify the direction of the magnetic field. So it will be from north to south in this direction, right? So in the same time, we'll draw the setup as well, right? So now they want to get the force, so which means current given magnetic field direction in the diagram, we need to deduce it. So they are asking the force direction, so which means three factors. So therefore, we are dealing with Fleming's left hand rule. We are dealing with the Fleming's left-hand rule. So now try to get the direction. So the wire is having the current in this direction. So current in this direction, magnetic field from left to right like this. Now use your left hand, place your finger. So FBI, the middle finger, give us the current direction. Index finger, magnetic field direction. So eventually you will get the force here. So therefore, they are asking us to draw an arrow to show the direction of the force on the wire. So I'm going to erase these parts. So we got the direction of the force. So it would be upwards like this, right? There will be a force acting upwards like this. Okay, easy, right? So these things cannot be determined just by going through the theory parts. So you need to place your fingers like this, and you need to judge the direction, right? You need to judge the direction. Okay, then all right. Yeah. Question number 13. Yeah, question number 13. So I will give you a few more minutes. Question number 13. All right. So the first few parts are smaller things, no? Easy ones, no? So I'll discuss, right? So the question is about electromagnetism. Diagram 1 shows the construction of an electromagnet. So there's a metal core, and there's a coil of wire. Name a suitable metal for the iron core. So you can use iron, right? Use a suitable metal for the iron core, you can use iron. State what must be done to the coil of wire to produce a magnetic field. State what must be done to the coil of wire to produce a magnetic field. So there must be a current, right? There must be a current flowing through the wire. There must be a current flowing through the wire. So always remember, without any sort of a current, there won't be any magnetic fields, right? There won't be any magnetic fields unless it is a permanent magnet, right? Unless it is a permanent magnet, if you need to generate a magnetic field around a wire, then definitely you need to conduct, you need to transfer current through it. Remember that part. Okay. Then part B, electromagnets are used in transformers to change the size of a voltage. So diagram 2 shows the construction of a simple transformer. Primary coil having 1500 turns, and the voltage and the current values are given. There's a metal core, and the secondary coil you can see 280 turns. So in the theory note, I mentioned that. So the voltage is directly proportional to the number of turns. So here you can see 1500 being reduced to 280. So which means definitely this is going to be a step down transformer, right? You are reducing the voltage. You are reducing the voltage. So from primary voltage to secondary voltage, you are reducing the voltage. So this is question number 13. Question number 13. Right. Then right. Then yeah. State the formula linking input or the primary voltage, output voltage, and the turns ratio for a transformer. So I'll use the word equation here, right? So here I can write the primary voltage. I'll use the symbols as well. So it is going to be VP over secondary voltage VS will be equal to number of turns in primary coil NP over number of turns in secondary coil NS. So you can write it like this. VP over VS equals NP over NS. Both are correct, right? Both are correct. The input voltage of this transformer is 115. So input means the primary value. So it is going to be 115. Show that the output voltage is approximately 20. So you are not going to apply that value, but you are going to do the calculation and you are going to get the answer something near 20, right? So which means we need to calculate the VS value, the output value, and the number of turns. So it is given in the equation 1500 over 280, right? 1500 and yeah. Then so you can subject the VS value. So VS value is going to be 115 into 280 divided by 1500. 1500. So now 115 into 280 divided by 1500. Yeah, the value is going to be something 21.467 volts, right? The input current for the transformer is 1.2. Input value, IP value. Calculate the output current. Assume that the transformer is 100% efficient, right? So now our equation VP into IP will be equal to VS into IS. VS into IS. So VP value, the input value 115. The input current 1.2. You need to calculate the output current. So I'm going to subject IS value. You need to divide it by the output voltage. So here the output value is approximately 20. You can use the answer 20 or you can use your answer 21.46. So in this case, I'm going to use 20. So here it will be 115 into 1.5, 1.2, 115 into 1.2 divided by 20. Output current will be 6.9 amperes. It will be 6.9 amperes. State two factors that would increase the output current of the transformer. State two factors that would increase the output current of the transformer. You need to use you need to increase the output current, not the output voltage, okay? Output current. So in order to get an increased output current, you can use less resistant coils, right? Less resistant coils. And also you can supply a higher primary volt value, a higher primary voltage, right? Higher primary voltage, and also you can use less resistant wires, right? Then we will go through another question. All right. Question number 15. No need of completing the question part A, but for homework you need to complete it, okay? I want you to get the answer for part B, this section, okay? Where you have the proton and the magnetic field. So they have given you the instruction as a use the left hand rule to determine the direction of the force acting on the proton. Explain how the force on the proton changes the proton moves through the magnetic field. You may draw the diagram to help. Okay, suggest why the velocity of the proton changes. Right. So try to get the answer for this section. I will give you a few more minutes. Only part B, from part B onwards. Yeah, only part B, question number 15. Only part B, question number 15. A proton moves through an uniform magnetic field produced by a strong electromagnet. The shaded area in the diagram represents the magnetic field. The initial velocity v of the proton is also shown. Magnetic field is acting into the page, right? So the magnetic field is acting into the page. The proton is moving from left to right in this direction, right? So here, the thing that you need to use, so they have given, use the left hand rule to determine the direction of the force acting on the proton. So the magnetic field, so in this case, so I can't draw the magnetic field which is going towards the paper. So therefore, I'll just imagine something like this. So this is the proton. Oh no, right. So the magnetic field is moving towards the paper like this, right? Now we need to know what will be the current direction, right? So in the theory note as well, I mentioned that. So if it is a positive charge, right? Positive charge. So if it is moving in this direction, so it will be the current direction as well, right? It will be the current direction as well. But the important fact, the most important special point, right? The important special point is that if it is a negative charge, right? Negative charge or any sort of an electron or something like that, then imagine, so the electron is moving in this direction with a velocity, but we consider that the current to be in the opposite direction, right? So that is the important fact here. But in this case, there's no need of so here it is a proton. So proton is a positive charge. So therefore, the current direction will be like this. So now you can place your fingers and see. So FBI, B is going towards the plane, current in this direction. So force will be acting upwards. So which means once after the proton is entered to this magnetic field, what will happen? There will be an upward force. So therefore, eventually the path will be like this, right? The path will be like this. And from here onwards, what will happen? So from here onwards, there's no any sort of a force acting. So therefore, it will be moving in a straight line like this. It will be moving in a straight line like this, right? So we discussed so many things about this thing in the last session as well, right? So use the left hand rule to determine the direction of the force acting on the proton. So the force acting will be upwards, right? Force acting will be upwards. Explain how the force on the proton changes as the proton moves through the magnetic field. You may add to the diagram to help you answer. So this is the diagram that you need to draw, right? So there's a force acting upwards, so which means the path will be changed and the path will be curved like this until it exits the magnetic field.
So
Suggest
how
by the way.
did you take that magnetic field direction?
Why it is given here? See, magnetic field is acting into the page. It is not going like, it is not coming towards you. So always remember, always analyze what is the magnetic field direction. So if it is given as crosses like this, then it is going towards the paper, right? So if we consider, just imagine this is an arrow, right? So in an arrow, what you have at the end, there are some feather-like structures, right? In movies you might have seen this type of arrows, right? So if we place the eye from here, what you will see, you will be seeing this pointy thing, right? So which means the pointy thing refers to coming, it is towards you, right? It is towards you. And if we place the eye from here, what you will see, so the arrow is going in this direction, so you will see those feather-like structures, right? So then you will see the cross like this, not the pointy head, right? Try to remember it like that. So this is going to be away from you, okay, away from you. So here it is mentioned the magnetic field is acting towards the paper. So that's why I draw this magnetic field like this. Otherwise, you can place the fingers and see. So the actual way is the magnetic field is going towards the paper like that. Okay. And suggest why the velocity of the proton changes. So since there's an external force, there will be a change in the velocity as well. And also here they are dealing with the velocity. Velocity. So here you can see velocity is a vector. So it is a vector. So vector means you are having the magnitude plus the direction as well. So the starting at the start, the velocity direction is like this. But once there's a force being acted, now the direction will constantly change, right? The direction will constantly change. Though the magnitude might stay as a constant value, but the direction is changing. So since the direction is changing, the vector, so the velocity value will also change. So that is the answer. Okay. the direction changes. Since the velocity is a vector, then the velocity value will be also changed. The magnitude might be a constant value. We don't know that, right? The magnitude, right? The value of the velocity might be a constant value, but the direction is changing, so therefore the velocity will be considered to be a changing value. Okay, right. Then question number 16, diagram shows the left hand. So they're asking what are the thumb, what is the thing that it is going to be given, right? And there's another question related to this thing. Yeah, we know how to calculate these sort of things. Yeah. For homework, try this question number 19. It is a good one. Uh, you need to think a little bit because here we are dealing with a scale and we are having a magnet placed upon the scale like this. So in this diagram, you can see the poles, right? South and south pole, which means like there will be an repulsion. So there will be a repulsion, right? So which means there will be a force acting downwards, like so. This magnet will be pushed away from the magnet A. So which means there will be an external force applied on the scale. So 16 newtons, there's a value given, right? So go through the question. Next week I will discuss it, right? This is a good question. The reason I need you to go through it. That's why I'm giving you to complete it for homework. Uh, and remember, it is a PR question from 2022, right? And these are some simple questions. Yeah, I think even we discussed about this thing as well. The magnetic field lines, right? And here also, same type of a question is given, right? They are asking you to explain the motion of the wire referred to the magnetic fields. Mm, yeah, shall we complete this section as well, right? So yeah, there's the current values given, magnetic field lines given. Draw arrows on the diagram to show the direction of the forces that acts on the coil due to the magnetic field. So once again, you are using the magnetic field, that Fleming's left hand rule. So here, the magnetic field direction in this way, current direction. So for X and W section, there will be a force acting downwards, and here there will be a force acting upwards. Yeah, those are the answers, right? Don't just copy the answer, just go through and try to get the answer, right? Try to determine the answer, try to improve yourselves, right? Explain the motion of the coil of the wire. So here you can see there are two forces acting on different directions. So which means the coil will be rotating in this direction, right? It will be rotating in this direction, something like a tap, right? Something like a tap, just imagine. So this is the upper part of the tap looking from the above, right? So you are applying a force in this direction. In the meantime, you are applying a force in this direction. So this is a fixed point. So what will happen? This thing will be rotated like this. Okay, something similar here, right? And here question number 24, they are asking you to judge which diagrams gives the correct magnetic field. So here you can see these two are wrong, and this is okay, this is wrong, and this is also wrong, right? Simple questions. And here, mm, what will happen to the magnets? So they will attract with each other, right? And here, which of these magnets are arranged to give given uniform magnetic field, right? Uniform magnetic field, wrong, right? You will be having something like this, right? You will be having something like this, and here it will be like this. Okay, just draw some field lines and see. what is going to be happen, right? And here you can see there will be an uniform magnetic field. This is okay. And here, so some might get the answer D, but here the correct answer is C. Clearly, you can get the answer C, right? This is some sort of a question thing, right? So, like, there might be a uniform magnetic field, but we consider there is no magnetic there's no uniform magnetic field there, right? So clearly, you can get the answer C easily. Then all right. We'll discuss this one. Question number 26, part A, non-needed. Part B, right? Question number 26, part B. Question number 26, part B. So there are two wires. I will label them as A and B, right? A and B. First wire and the second wire. So the directions, the arrowhead, they show us the direction of the current, right? They show us the direction of the current. The current in both wires is in the downward direction. The student observes that the wires move towards each other. Move towards each other. Towards each other means like we can get an idea that there are forces acting like this, right? Attraction forces. Explain why the wires move towards each other. Explain why the wires are moving towards each other. Yeah. So here, this is a good question actually, right? So in order to explain it, I'll draw a separate diagram like this, right? So this is wire A, this is wire B, and these are the direction of the currents, right? Okay. So now the thing that they have given is only the current, right? So therefore, but they haven't mentioned anything about the magnetic field, right? So current is given, nothing mentioned about the magnetic field, but also they have given that these wires will be attracting towards each other. So which means they have like in a different way they have mentioned about the force as well, right? In a different way they have mentioned about the force as well, right? So what we can do. So since you are having a current, so you can see that there will be a magnetic force generated around wire A. So if we apply the right hand swirl rule, right, then we can judge that there will be a magnetic field around A like this, right? So same magnetic field lines will be also going through this B wire as well, right? Same magnetic field lines. So which means if we consider B here, current downwards and the magnetic field lines are going like this. So which means if we observe from here, we will be able to see that the magnetic field is pointing towards you, right? It is pointing towards you. So I'll draw it like this, right? So the magnetic field is pointing towards you. Okay. So now use the Fleming's left-hand rule on B. Fleming's left-hand rule on the wire B. So FBI, so which means the index finger will be pointing towards you. Current will be downwards. So eventually there will be a force on the left-hand side. So this is for wire B. Right. Now we'll consider about wire A. So now we are going to consider about B. Once again, the magnetic field will be in this direction, right? Oh, wait, no, the other way. Sorry. So the magnetic field will be in this way, right? So if we consider there will be a magnetic field line because of B acting on A like this, right? There will be a magnetic field line like this. So if we consider wire A, if we consider wire A, current is pointing downwards, okay? Then the magnetic field line, so if we observe from here, you can see the magnetic field is going like this, right? It is going through the wire towards the plane. So then it will be across like this, right? It should be across like that. So FBI, then you can see there's a force generated in this direction, right? There's a force generated in this direction. So which means eventually at this point, right? At this point, there will be a force in this direction. And also here there will be a force in this direction. So there are forces acting like this. So eventually what will happen, these wires will be attracted towards each other, right? The wires will be attracted towards each other. Tell me whether you got how the method of deducing that answer. Yeah, great. Okay, good. Right? So this is a good question. That's why I use this diagram and explain so much about it. Okay, so this was a good question. And see, a recent paper, right? 2023. Okay, so you will be getting similar questions in the exam, right? Okay, then question number 27 also, we need to use the magnetic field that Fleming's left-hand rule. So you can, okay, so the symbol shows, all right. Question 27, diagram 1 shows some apparatus used to demonstrate the magnetic force on a current carrying wire in a magnetic field. Okay, so there are nothing mentioned about the magnetic field direction or the current direction. Then diagram 2 shows 4 different arrangements of the apparatus. The symbol, this thing, shows that the current is directed out of the page. It is directed out of the page, which means it is coming towards you, right? Now, there are 4 arrangements given. Which arrangement of the apparatus will cause there to be an upward magnetic force? Upward magnetic force on the wire. So, already they have given the force direction. So, you need to place your thumb like that. So if it is the force in this direction, right? So the magnetic field can be in this direction and the current will be pointing towards you, right? So in all of these 4 arrangements, the current is pointing towards you, right? So this is going to be our arrangement. So which means the magnetic field from left to right, which means the north to south will be arranged in like this, right? The arrangement from north to south will be like this. And the current is coming towards you. So our answer is W. Easy, right? It is easy. And even here, by looking at these diagrams, you can easily judge. So here you can see 2 north poles are arranged. So definitely this is not going to happen. And here you can see 2 south poles are arranged. So again, definitely this is not going to happen. So you need to judge with the X and Y configuration just by using the diagram, then you can easily get the answer there, right? So our answer is W. And the other ones are easy questions just to calculate and change the values. And question 28 is good, right? It is good. Try it. Try that for homework. So in this case, we are dealing with momentum as well, but here we have placed some magnets on the gliders. So which means like there's a if there's an attraction force, so these gliders will attract each other, right? They will be collided. But just imagine you are using same poles on north and north, something like that. Then there will be a repulsion force. So therefore, the gliders will be repelled from each other, right? So this is a good question. So please go through that. Complete it for homework. I will discuss that next week. Okay, so go through the question properly and try to complete it. Yeah, we know how to calculate these stuff. We discussed about these stuff in waves and that section. So try to complete them. And here also some easy peasy things are being asked. So this question is also good. Question number 30, right? There are so many questions that you can go through. So try to complete them, right? Try to complete them within this week. Yeah. And here we can see there's a national grid related question is given, and even I discussed about this that equation as well. So you can go through it. Similar questions are given, right? Similar questions are given. Yeah, see here, similar questions are given. So in this one, they are asking what is the magnetic field direction, right? So they have given the force direction, the velocity direction. So from the velocity direction, you can get the current direction. So the third factor, they are asking what will be the magnetic field direction if there's a force acting in this direction. So easy question, always like, try to get familiar with the Fleming's left-hand rule, right? Try to get familiar with the Fleming's left-hand rule. Most of the time they will ask questions related to that. And here also energy related questions when it comes to transformers. Yeah. Yeah, same questions, right? Yeah. Here, this is a good question, okay? So please go through them. So for the moment, you can't complete this one. The reason is we need to discuss the next topic as well, that the radioactivity related stuff, then you can easily go through these reactor questions. And here, yeah, turbine and all the related stuff are given, right? Okay. So here also a transformer is given, right? So please engage in these questions and try to complete them, okay? So for today, I'm going to conclude the session now. So today I my goal was to complete the theory part and to engage in some of the questions to discuss with you guys. So please go through the question papers, question tutorials. So it is your duty to complete them, okay? So I can just discuss them and you will be just looking at the screen and you will be looking how to calculate this stuff. But you are the guys that you need to engage in these questions. So you need to train your brain to grab these data points, and you need to train your brain to use these applications easily, right? Without being going here and there just to extract the data and to complete these questions, right? So please engage in that work. So within this week and try to complete many questions as possible, right? So I will discuss some chosen ones next week also, and we can start the next lesson as well, right? So I'll drop a message on the WhatsApp group, whether mentioning whether we are going to start the next topic or we are going to discuss the session, right? Okay, so that's all for today. So please go through the questions and please go through the questions. Okay, right. So thank you for